We've got shaded triangles here in the 2023 AMC problem 24. Isosceles triangle ABC has equal side lengths AB and BC. This is equal to this. In the figure below, segments are drawn parallel to AC so that the shaded portions of ABC have the same area. So this area is the same as this area. The height of the two unshaded portions are 11 and 5 as seen in the diagram. What is the height of H of ABC? Cool. So this has a height of H. This has a height of H. Notice that these are the same triangles. And notice that we've got parallel lines here. This is drawn parallel. And when you see parallel lines, it's almost always a sign, especially in this kind of configuration, to use similar triangles. So because this whole height is H, and this top part over here is 11, we would have that this over here is H minus 11, because the whole thing is H and the top part is 11. Similarly, this whole thing is H, and this bottom part is 5. So this over here will be H minus 5. Okay, now what condition have we not used yet? This condition of same area. This shaded area is the same as this shaded area. How should we find the area? To find area, we need base times height for a triangle. We don't know any of those. So the key here is we're not trying to find any specific area, just the ratios. So, like I mentioned earlier, parallel lines mean similar triangles. And notice that this triangle will be similar to this triangle by parallel lines, and you can derive using AA similarity if you'd like. This angle and this angle are equal by corresponding in the shared angle. And similarly, we have this triangle is similar to this triangle by the exact same reason. So let's try and use this similarity to our advantage. So the only thing common about these two diagrams is the ABC. Notice that even though it might look like it, this is not the same line. It's a little bit tricky here, but this line is actually a little bit above this line. So they're not the same line in the triangle. So the only thing common about these two diagrams is ABC. So with these let's first look at this similar triangle pair. Let's first look at this similar triangle pair. How should we relate the area of the shaded region? Well, the trick for this types of problems is we're going to have to relate the area of the shaded region to the area of the entire triangle. Because like I mentioned earlier, the only thing common about these diagrams is the big triangle. So to find the ratio of the areas of these shaded regions, it's going to be much easier to find the ratio of the areas of this region to the area of the entire triangle. And similarly, find the ratio of the area of this region to the entire triangle as well. So what is the ratio of the area of this region to the entire triangle? Well, to do this, we use similar triangles. What is the scale factor of similarity? Well, notice that this is 11 and this is H. And remember that similar triangles not only preserves the same side length ratios, but everything on the inside as well, including height. So let's say the ratio of the red triangle to the blue triangle is, well, the ratio of side lengths is 11 to H. So therefore, remember that area is similar ratio squared. So the ratio of the areas is the ratio of the side lengths or height or whatever lengths in the triangle squared. So that therefore, the ratio of the area of the red region to the area of the blue region of the blue triangle, as I drew there, is just the square of the ratio of the side length. So 11 over H squared, which is 121 over H squared. Okay, so that's the ratio of the red triangle to the blue triangle. But we're looking for let's erase the red and blue. we were looking for the ratio of this shaded region to the area of the entire triangle. So notice that the red triangle that I had over here, it was red, remember? The ratio of that red triangle to the entire triangle, blue triangle, we already found to be 121 over h squared. But we're trying to find the ratio of this gray region. And notice that this gray region is just the area of this entire triangle minus the area of the red triangle. So area of blue triangle minus the area of the red triangle, that is the area, this is the area of the shaded region here. We're talking about the first diagram here, just to be clear. So the area of the blue region minus the area of the red region, that is the shaded region. But remember, we're trying to find the only thing common about these two diagrams was that the original base triangle was the same. So what we're going to want to do here is relate the area of the shaded region to the area of the entire triangle, or the blue triangle. If you remember, that was the entire triangle. So the blue triangle was the entire triangle. So to do this, we just do shaded region, which is area of blue minus red triangle, over the area of the blue triangle. Right? Because notice that this part is equal to shaded, and this is the area of the blue triangle. So this is equal to the area of the shaded region over the entire triangle. And we can simplify this to get, well, notice that this and this, well, we can divide that out to get 1 minus the area of the red triangle over the area of the blue triangle. And this is, of course, area here. And we already found this quantity, ratio of the area of red to blue, to be 121 over h squared. So this is just 1 over 121 minus h squared equals h squared minus 121 over h squared. So that is the ratio of the shaded triangle, or the shaded trapezoid, I should say, to the entire triangle in the first picture. Now what about the second picture? Let's make this a bit smaller so we have some space to work. Put this aside. Okay, so over here, it's something very similar. We have similar triangles. So the ratio of the shaded triangle to the, let's call it the entire blue triangle, because they're the same triangle, the shaded to blue, shaded, I'm just going to make it black, to the entire blue triangle is, not the area, just the side length ratio, is h minus 5 to h, because remember that height ratios are the same as the similarity factor. It's not just side length ratios. Height ratios are included as well. So therefore, if you're looking at area, which I'm just going to write as A for now, for shortcut, A of this region over the area of the blue region is squared, because the area proportionality is the side length or height squared. So this becomes h minus 5 squared over h squared. Okay, but so this is the ratio of the area of the shaded trapezoid to the entire triangle. And this is the ratio of the area of the shaded triangle to the entire triangle as well. But we're given that these areas are equal. So notice that, oh, this is the ratio of the area of this over here is the ratio of this triangle to the entire triangle. This over here is the ratio of this triangle to the entire, or this trapezoid, sorry, to the entire triangle. What does that mean? Well, if their areas are equal, so are their ratios of the areas to the big triangle, since the big triangle are the same. So that means that h squared minus 121 over h squared equals h minus 5 squared over h squared. Because, just to mention again, this is the ratio of this to this. This is the ratio of this over here is the ratio of this area to this. So, and we're given in the problem that these regions have the same area. So the ratios of their area to the big triangle, and notice that they're the same big triangle, is also going to be the same. And now we just have a simple equation. H is non-zero, so we can just write it as h squared minus 121 equals h minus 5 squared, which is h squared minus 10h plus 25. We cancel out h squared. We get that 10h is 146. Our answer is 14.6. And we are done.